world. I'm back. I thought we would take another look at 52. So I did, I looked at it for a minute after the stream and was able to confirm. So just a real quick review before I leap into it. 52, which is on the screen there, you can just read it. But 52 doesn't seem to rely on the previous couple problems, 50 and 51, although it's a similar flavor. Wants you to find the coefficients Ci, right, for this series. And it looks almost normal, right? It's got odd powers of Q in front of each Z. But we also got reciprocals, which makes it a little spicy. I guess that also makes it symmetric, so you're able to just get the identical values for the CIs. The CIs are effectively even. So it wants you to solve for CI. And the way I had done it, which I still think will eventually work, I started to rewrite my finite case. Well, I had done it in an infinite case because I just wasn't paying attention. But what I had done was I ignored the reciprocal for the moment, and I said, what if we just had z, 1 plus qz, 1 plus q cubed z, 1 plus q to the 5z, etc. So what he's going to call phi n in his solution is my f times g, where g is f of 1 over z. So it's the same function, but with a reciprocal. So my idea was to take the product of that, like get a grip on these coefficients for this f function, and then take the product of that with, take its power series and take the product with like its reciprocal. Well, I shouldn't call it reciprocal, but f of the reciprocal. So take the product of f and g, and you'll get a series, and you should be able to write down what those coefficients are, at the very least in terms of products, right? I still think that's going to work. I'm pretty sure. So one thing that we could do is try to verify that I get the same thing he gets. And for some reason, on my last stream, when I tried to verify his functional equation, I had like a number wrong. I was like missing a negative sign. But then I checked it afterward, and it was fine. So I was able to verify his... I guess basically this. That if you plug in q squared z, you get the original function times, then you get this stuff. So I could show you that. And I even, here's just some scribbles with me playing with the coefficients. I was even able to confirm his recursive relation that defines the CKs. I didn't solve it. He actually solves it. He gets something like, where is it? He gets this as an answer. I was able to confirm the Q part. And even with my own version of it, I get the Q part and I get the denominator. But I don't get exactly the same form for the numerator, although I haven't really finished checking it. Hey, what's going on, Stucky? Good to see you, Stucky. I got your message. I'll write you back. But, yeah, are magic series a thing? Let me Google this. Sounds like it should be a thing. Magic series. It's probably just going to pop up magic squares or something. A magic series is a set of distinct positive integers that add up to the magic the magic square. Okay. Yeah. Of course, magic series is an actual thing. Maurice Krejcik. Here, I can... Oh, you can't see it. Wonk. Magic series. Cool. Walter Trump. Oops. Yeah. Interesting. Intriguing. Wait, what? Retired in 2015. Oh, yeah, he's a pretty young guy. Okay. All right. interesting. Well, yeah, I'll try to pop in tomorrow to your thing, Stucky. I mean, I'll just text you back. We don't have to talk about it right now. But yeah, mostly I just didn't really know what you're, I don't know. I didn't know what you were doing, like how the structure of things are going, and I wasn't about to butt in with my confusing questions. Although I am sure you would welcome them. But all right, so I'm kind of tired of this question, but I'm also, it seems like a really, yeah, you can't see it there, but the next, oops, the next few questions are really kind of awesome. So like after you get through, 52 is the one that I'm finding is to be, I thought it was a bear yesterday. Today I'm like, it's really just bookkeeping. This is not as bad as it looks, honestly. It's probably what they would call a straightforward but tedious computation, okay? So 52 is not really anything to be scared of. And I think 53, because he says just deduce, so probably these couple, oh, maybe you can see it. Yeah, I really like 53. It's like, it's looking at this infinite series where the coefficient is q to the n squared. I just thought that was like a really pretty, that's like a pretty series. Of course, actually evaluating it at 1, for instance, for z, I mean, is it so important what it equals? It's just kind of cool that it equals this product. Maybe that's not very practical, actually, now that I think about it. How are you going to actually use that? But I think those formulas pop up now and then. The other ones I'm not as impressed with. That's a cool one. Q to the sum gives you this sequence, this product. Anyway, I don't know. I'm betting these all somehow follow from this junk that we're doing up here in 52. So even though I kind of hated 52 yesterday, it seems like a rich like source of other series, like other identities. And then 56 is kind of the same flavor. I hope it also somehow falls out from this junk that we're working on today. But I don't imagine it's going to keep going that way. 57 looks like a fresh problem. 58 is just 57 again. 59 is just a new one. Use it to derive a power series for log. So yeah, they start to get a little different again once we hit 57. But I think 53 through 56 are going to be hopefully applications of 52. So I'm going to take another stab at 52 for a little while until I get tired of it today. I don't know why. I'm just hoping that it is, I don't know. Because I did work on it yesterday, and immediately I got something simpler, like I got his answer. So it can't be that bad, right? But again, I think the way I did it seems like it should work. Maybe I won't rewrite it all. I'll just show you what I was thinking. So here was my way to do that problem, 52. Let's write that down, I guess, 52. So here's the way that I approached it. I do get this relation, although I have a different function than he does. What was his relation? Let's see real quick. His was so this is what I got for my function. Mine's different than his. Mine is just the positive powers of z, no reciprocals, okay? So it's the same function as this, but half of the factors are missing because I don't include the reciprocal terms. So for his actual question for 52, he has what he calls phi n. You basically q to the 1, q cubed, q to the 5, etc., up through q to the 2n minus 1. And he does that both for z and for and for the reciprocal of z. And for him, he gets this functional equation where if you were to plug in q squared z instead of just z, if you plug in q squared z in place of z, you get this. On mine, you can see I get something slightly, oh, mine's backwards. Okay, so good. So I get the same numerator, and my denominator is a little bit different. Okay, you see that? My denominator is 1 plus qz, whereas his denominator is qz plus q to the 2n. So, fine, right? They're different functions. Of course, it's a different functional relation, different functional equation. But I just thought it was funny how very similar, like, it's very similar. Okay, so now I'm going to use this functional equation, and I'm going to assume that my f is right here. I have a power series rep for f of z. All right, and one thing you can observe immediately is if you plug z equals 0, f of 0 will be a naught. F of 0 will also be 1. So I jotted that down somewhere. But a naught should be 1. And actually, in the actual question, c naught would also be 1, right? If you plug in, well, no. I thought it was 1. I can't actually plug in 0, right? I can't actually take phi n of 0. It doesn't make any sense. So that's one hang up I have. And actually, I'll bet if you look at his answer, here it is. If you plug in 0 to this formula for all the v's, 1 minus q to the n, 2n. So all the v's are 0, like 2n plus 2, 2n plus 4, up to 4n. This is a q to the 0, of course. So he doesn't get 1. I mean, I don't believe. Maybe he does, and I just can't see it. 2n plus 2, and downstairs you get 2n. So they're actually missing each other. There's no overlap here. They don't cancel. This starts at 2n plus 2, and it increases by 2 each time until it stops at 4n. Downstairs, I start at 2, and I end at 2n. And so he has an answer for C0. Should I write that down? Just, I don't know. I'll write it somewhere else because it's not particularly... but his... I mean, I don't need... It's a different notation. I don't need to call it his. But C0 would be... thought I had some juice in this pen. His C0 is 1 minus q to the 2n plus 2, 1 minus, all right, F this. His C0, okay, is 1 minus q to the 2n plus 2. I bet you can't really read that. 1 minus q to the 2n plus 4, up to 1 minus q to the 4n. And then downstairs, it ends on the term just below this, 1 minus q to the 2n. Starts at 1 minus q squared and goes up, etc. Also, he has a q to the 0 over here. So that's his first term, his constant term is this mess. Anyway, let me get back to my story. So the way I was doing it, I ignored the reciprocals. Instead, I treat them as two separate power series, and I'm going to take the product of the two. Okay? So we know a nice formula for that, especially because it's finite. When you do that out, because it's finite, when you do that out, you know, it stops on the nth term. Like, if you let I be n plus 1, you don't get anything, you just get 0. So we do get this sort of we get this sort of formula, but it's nice because there's a finite number of terms. It just goes from 0 to n. So the only thing missing now is I skipped a couple steps here, but if you assume that remember this, mine is slightly different than his because I'm looking at a slightly different situation. I'm looking at f instead of phi n, I guess. I called it f. So I do have a slightly different functional equation here. But anyway, so assume that your f has this power series rep and use your equation. We're going to plug in q squared z into the power series. That's this right-hand side. You can't read any of this, can you? So I'm just doing that. And so left-hand side is 1 plus q to the 2n plus 1. That's that part. Right-hand side is 1 plus qz. Right? You do get some extra terms. So like when you scale by z, you're adding 1 to this power, right? If you re-index, you're going to get, instead of ak, you get ak minus 1. Oh, there you go, ak minus 1. So this is this. So because of that, I basically just wanted to equate the stuff when the index goes from 1 to, say, n minus 1. So like I dropped the 0 term and I dropped the n plus 1 term. So there's going to be some extraneous stuff where I remove n plus 1 from here and I remove 0 from the first sum. So extra stuff plus the middle, extra stuff plus the middle, and you can then equate these inside guys, okay? We got lucky enough that the extra stuff just equals the extra stuff. So a naught equals a naught. And believe it or not, the coefficient of z to the n plus 1 is also equal. So I didn't make any mistakes. Then just equate these coefficients, right? You get this statement. You can use that to solve, well, so I get something really similar to his. Again, it's a little different. But also it should be a little different, right? Because it's a different function. So I end up with this in general. And remember, we know that a naught is 1. So you can start computing these guys. I did that maybe down here. So for instance, a2, well, here's a1. And then a2 would just be the next term up. I don't know how well you can read that. So this is an example of a2. And that's where the q to the n squared is coming from. You got q times q cubed times q to the 5th, etc. So the exponents, when you sum those odd numbers, you're going to get q to the, well, it depends on how high up you go. But you're just basically getting q to the k squared for a sub k. Downstairs, you're getting 2 factors in the case of 2. So you're getting k factors in general, and they look like, well, they look an awful lot like these downstairs here, right? And this is the actual correct answer. It's a slightly different function. So I don't know. Maybe I shouldn't spend any more time. I'm just showing you what I did off stream. So my last step, if we were doing it my approach, the last step that I would have to take is trying to solve for these CMs, right? I have to finish this. We've got a nice, I say nice, but we've got a formula for the CMs, but unfortunately it involves products of these AKs that I started to write down. AK in general, it's not just a power, it's k iterations of stuff that looks like this, you know? So this is A2. So you use this formula. I should have written it as a product. I was confused when I jotted it down. Yeah, it's a product, not a, you know. So it's the product of these as this variable goes from, say, 1 to k. It does have k factors. And so you can see, like, you can simplify the q part. So maybe I should try to write that down, but I mean, you can kind of see what it is. These powers decrease. So on 2 you get first term, and then on the second term you get 2n minus 2 upstairs. But yeah, so you can see why I started to hesitate, because the CMs, they're not just like a product of two of them. It's like a series. I guess, I mean, it is true that they're equal. So I was able to see that they're symmetric. C1 is equal to C negative 1. You can see that. Cn is equal to C negative n. So it is symmetric like it's supposed to be. In fact, and my C0 is not 1, just like I was saying it's not supposed to be. I wrote it down for his, right, just a few seconds ago. I wrote down C0 would be, here it is. His C0 would be this junk. He also has a q to the 0 out front, right? Now, unfortunately, mine is a sum of squares, but the denominator, that last term, has the biggest denominator, and of course it shares factors with all of the others. So it's certainly possible to write, and what is that denominator? It's going to be the same denominator that you saw in the answer. It's q squared, q to the 4, all the way up to q to the 2. Let's see. Should be q to the 2 times whatever, so q to the 2 times n. So we have the same denominator. Let's see. A naught squared is, well, a naught is actually 1, so that's the number 1. But a1 squared is this term squared, 1 minus q to the 2n. You think maybe this has something to do with that? That's 2n squared. I don't know, because we have many more terms to deal with. I would think, anyway, you can see why I'm starting to slow down on this. I didn't actually verify his. I was able to verify this, but I didn't actually solve for CV. You know? Partly that involves I need C0, and then I need to iterate this recursive relation a bunch of times, right? V times, and then I'll have this formula. I can sort of verify this part and the denominator. The numerator is what's given me a little bit of trouble. But that makes sense, right? That's the hard part. Yeah. Anyway, now you're all caught up. Can't believe that took me 20 minutes to explain, and I still didn't actually solve the problem. But yeah, that's now you're seeing where my head is at for number 52. I still really believe my approach works. So I guess there was nothing wrong with what I did, but at the end here, I'm like, oh, okay, great. Now I got to solve these somehow. I mean, there's nothing, these don't really change. They're all just shifts. But then you sum over them. That's what also kind of sucks. So even if I had a general formula for this kind of thing, I then have to sum it. Yeah. Well, well, well. Yeah, I'm almost not in the mood to redo this computation. I scribbled all over it so you can't see what I did, but but I basically said, all right, here's his relation, and then we expand it using this power series for phi n. Oops, sorry here. We expand it, right? This is the power series expanded. You got q to the 2n plus 1z. That's right there. And so it results in this shift. And then I had to have a bunch of extraneous terms, anything where k is either n plus 1 or k is 0. You want to kick those all out. But yada, yada, yada. If you equate the coefficients in front of z to the k or in front of z to the negative k, you can't see any of this. Z to the negative k, and there's my other z to the negative k. If you equate those, you actually do get the relation that he wrote down. You do get this. So it gives you a way to solve for the ck's, although again, I don't know c0. And my formula for c0 didn't make any sense. I had a formula for c0 in terms of like c1, which should have been consistent, but it didn't make any sense. So I don't know if I made a mistake. I don't want to get burnt out on this, but also 53 is like a very similar flavor, so I don't know if I can even do it without... What is 53? Let's see. Deduce the following from 52 by taking the limit. So he's got 3 factors in here. He lets n go from 1 to infinity. Okay, sure. So that's the same, on the left at least, that's the same series he had. Don't know where these are coming from. That's a problem, right? These are coming clearly from the denominator of the, the c, the coefficients for c above this. Okay. I mean, I guess. But I still don't get how this is... Yeah, I don't quite see this. What is his answer then? He's probably not going to say anything. Yep, he doesn't say anything. He says, take the limit. Haha. Okay. Same thing with 54. He has basically no comment. He says, special case 53. Does that say q divides q to the 3/2? What are you talking about? Is that supposed to be like replace q with q to the 3/2? What's 54? Man, this book is beating me up lately. I don't know what this symbol is supposed to mean in this context. But yeah, replace z with negative q to the 1/2. I don't know what on earth this is supposed to be. Was he saying replace q with q to the... He would say that, though. Is he saying q or q to the 3/2? Probably not. I don't want to give up. I kind of just want to finish these next 5 problems and then move on in the next couple days. But I'm having a hard time with these. All right, let's look back at his answer. In 52, I was able to pretty much confirm this. I didn't really understand that part. I did not confirm that part, right? I don't think I did. I did confirm this relation though. So he says you get this, and that I didn't really follow. Although when I looked at my work, I had gotten the same denominator and coefficient, but I don't get the numerator. My numerator looks a little different. But then again, mine had better look different because it's not the same formula. Yeah. So, I guess I got to make a decision. Do we continue plotting away with 52? I mean, it doesn't look like I'm going to make a lot of headway on 53 either, huh? Do we start over? Could always start over. I'm going to continue doing it my way and see if I get his formula, okay? So the stuff I was talking about for 20 minutes at the beginning here, yada yada, I felt pretty good about it. The only thing that fell apart was down here. This is not exactly the right formula. I should have written this as a product. So let's suppose that, I'll just sort of restate what I'm doing here at the top. And I do a finite version of this. So we stop after n factors. We let gz be f of 1 over z. And we want to look at the product of 2 power series, f times g, where you assume that the coefficients are ak. So here's fg. And if we do that correctly, it should actually match his, I'm going to just call him ck, okay? But the c's are actually even. I was able to verify that part. Yeah. So some stuff that we know, for instance, is this is a formula for the CMs, or for these coefficients C. C0, for instance, is the sum, and A naught is 0, or sorry, 1, excuse me. And like Cn is An. But I already written down a few of these just to sort of give you the flavor. You can see that this is why it would be symmetric. So c to the negative 1 is the same as c to the 1. Cn is the same as c negative n. C negative n is actually A0 AN. So this formula always works, even for negative m. All right, what else did I know? So the last thing that I was able to deduce, I'm going to spare us the gory details, but we're just equating, maybe I'll write down the relation. If you plug in q squared z instead of z, you can verify that this happens. And if you let f be this power series, and you use your relation, you will able to conclude that this is how the AIs behave. You get a formula like this. And yeah, so when you have this formula, that's this part. I actually first got this, and then I shifted it by 1. That shifting by 1 was kind of interesting. It turned 2k minus 1 into 2k plus 1, and suddenly didn't match up perfectly with his answer. But my numerator is wrong anyway for his answer, because it's a different function, so I don't know, maybe that doesn't matter. But I'm writing it with the 2k plus 1. So that's what I got. And now the last part is, if you solve for this in general, because we know that a naught is 1, right? So a1 would be just, a1 would just be this series with k equal to 0. We can do that out if you want. A1 would be 1 times, and then this with just k equal to 0. Right? And then A2 is the same thing, but you plug in k equal to 1. And A3 is the same thing, another factor, but you just plug in k equal to 2, etc. So we're getting yes, we're still just talking about the AKs, not even got to the Cs yet. But yeah, if you iterate this, you can get a nice product for your answer. It's q to the, I'm just going to write this again, you let k go from 0. Oops, that's a bad notation, isn't it? Let's make it v, I guess. V goes from 0 to k. Huh. Maybe we should make this plus 1 so that it matches up correctly, So I don't have to do any subtracting. Because this is confusing already. So let's make this k plus 1. Anyway, so the first term was just q to the 1. Put a q to the 2k plus 1 here, times 1 minus q. I'm just copying this. Yeah, that's it. It's this product now. Now the nice thing is, these q's, I can see that that's the sum of odd numbers. So I can see this part. Oh, damn it. I meant to write v's here. Bad work, Dave. Bad work. All right. So I can see that we're summing up the first k odd numbers. So for instance, A2, you get, the last term you should see is k equal to 1, or v equal to 1, I should say. You get q times q cubed. So the total is q to the 4, which is, I guess it's v plus 1 squared. Like the next time we're going to get 9. That's when v is 2. Or I should say k is 2. It's like the last term that you see. So for A3, anyway, if you stop at k, lost my train of thought there. But yeah, A1 is this. A2, like when k is 1, you get 4. So when k is 2, you get 9. So it looks like we're getting k plus 1 squared, right? Anyway, we still have his other junk. He doesn't even, well, his answer has these big products. He just wrote out the factors, you know? So I don't need to get a perfect form for this stuff. The only one that he consolidated was this leading, this Q. So maybe I shouldn't even think about trying to do more. But, you know, we could at least visualize it a little bit, right? So we stop at k, that's 2n minus 2k. That's the last factor that you see upstairs. Downstairs, very similar. When v is 0, you just get q squared. And we stop when v equals k. That's 2k plus 2. Sure. Weird. These are going down. These apparently do not overlap. I don't know why they wouldn't. And like, what about when k equals, say, n? Do we ever get that? Yeah, we should. So when k equals n, they do overlap, right? Actually, no, they don't. Yeah, they do. This is 0. This is 1 minus q to the 0. So there's definitely some pretty heavy overlap by the time you get to qn. But at least these are like, they're both even, so it's conceivable that there's some cancellation. So for instance, like n minus 1, you're getting 1 minus q squared, and you see that here. Yep. Anyway, that's my formula for ak plus 1. If it had just been ak, I suppose... I mean, obviously we can just write the same thing and decrease this by 1, but I was wondering if I can, like, tweak the formula, but maybe that's a bad idea. You know, I was going to do some sort of shifting. Because in his answer, for instance, he probably has this, and then he has like minus 2. You know, he's got stuff like that. He's not afraid to write it in the middle of the formula. He starts at that term. Anyway, looks different than mine. But that's all right. Mine is not the same as his question. So if I did take these products, and I had a product of two things that looked like this. Yikes. Don't think he has any... He doesn't have any sums like I do, you know? Because I split mine up, I end up with these... All right, I kind of want to save this since it doesn't look like trash yet. How are we gonna do this? Sure. So, all right, let's at least, I mean, my Cn term, he had said Cn was like just the q part. He got just q to the n squared. But mine, well, I didn't do it yet. Mine is just an. Mine is literally just one of these. It's like this, but with an n in place of k. So we should look at that. I also wanted to look at C0, and then if I still have any brain left in me. So what is a n, for example? According to my formula, it's supposed to be q to the n plus 1 squared. That's already a mistake, right? Great. Right? Doesn't his answer say q squared, q to the n squared? Huh. Oh, I'm wrong. Good. Sorry. I was looking at k plus 1. So I need to remember to stop early on this. Sorry. So we actually agree on that part. Q to the n squared. But I need to show that the rest of this cancels out to be 1 somehow. In this particular case, when you're looking at k minus 1, or sorry, n minus 1, excuse me. And we already saw that this cancels. These are the same. And these are increasing by 2. Huh. Is it going to be obvious? If you let k be n minus 1, you get 2n. Wow, it is 1. No shit. He's right. I got the same Cn as him using my formula. It's, wow, okay, it works. Huh. So we got Cn down. I'm completely shocked that that worked. I want to look at C0 and like C1. Those are going to be maybe the worst of them. I still don't have a nice general formula, but, you know, I'm doing them in practice. I mean, I realize this is a formula, but it's just not it's not as nice as what he has as a final answer. So I'd like to verify that my method still worked, if I could only just get through it. All right, C0. What I have as a formula for C0 is this sum of squares of and I just sort of verified that an really does cancel and give you q to the n squared. So this last one is, I mean, doesn't that make you think maybe other stuff cancels too? I don't know. They didn't really cancel that nicely. Shouldn't they all cancel except for the first term, though? That would be really helpful right now. So maybe I should look at an minus 1, because that's the one that's going to, you know, this doesn't cancel. Yeah, let's see what it does. Let's see what it does before I think about this one. An minus 1 would be q to the, let's see. It's basically this formula, but we're subtracting 2 this time. So this is n minus 1 squared. This stays the same. These factors stay the same, but we stop at k minus 2, okay? So we get terms on top like this. But the one that we stop on is actually 2n, and then instead of k, we're going to replace this with k minus 2. I'll figure out what that is in a second. And then downstairs, I mean, it's minus 2k, what, plus 4? So 2n minus 2k plus 4 is where we're, oh, you can't see it, plus 4 is where we're stopping. Downstairs we have 1 minus q squared. That's coming from like a1. 1 minus q4, that's coming from a2. Da 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 da. And then we stop at, and this is what you get when you plug in k plus 1. So I actually want to plug in k minus 1, basically into this for k. This is k plus 1, it gives you this. So I should get 2k minus 2, right? Yeah. I meant n. Yeah, why do I have k's? I'm a little confused for a second here. These are supposed to be n, right? 2n. Yeah, this is supposed to be n instead of k. Okay? Because I'm actually plugging n into my formula. So if you plug in n minus 1 into this formula, I realize it's a little confusing because my formula was in terms of k plus 1, but 2 minus 2. So it stops at 1 minus q squared. That can't be right. Oh, no, it doesn't. It stops at this one. It stops at this one, which is what I thought it would do. It stops at 1 minus q to the 2 times 2. That's the last factor you see upstairs. So this cancels with that. And then here I've got 2n minus 2. This cancels with that. This is what I kind of thought would happen, right? Obviously, I was sort of expecting that is what I was hoping would happen. But I know that a naught is 1. Why would that be? Shouldn't I have a bunch of... How could they cancel with this thing? Oh, you know what? I can't use this formula for a naught. I probably can't use this formula for a0. It doesn't make any sense. So don't worry about that. Yeah. It works for a1, but I can't just plug a 0 in here and expect it to make any sense. So never mind. Yeah, okay. You don't use this formula to interpret what's happening with a sub 0. That's the one coefficient that it doesn't work for. Okay. So this is kind of neat that it did what I sort of expected. So can we think about this now? Yikes. Because we're going to be squaring this and summing them. So it's q to the 2. Like one of the terms that you get, oh no, you're summing them. Yikes. Huh. This should be obvious that this. Wait, wouldn't this be the same thing that I get at 1? Why did this happen? Like, my formula. Yeah. You see what I'm saying? Since this is the same formula as this can't be an as well as a1. I mean, I realize the q's are different. The coefficient out front is different, but like, I must have done something wrong here, right? For -1, we sort of stopped short, but I saw that this matched up, and this matched up, which is what I was expecting. Huh. I guess I just really hadn't noticed that that's the same formula coming from the other direction. Except for the Q out front is different, of course. I guess that's a good thing. You think we're ready to tackle this guy? Oof. In a sense, this is one of the worst ones because it involves all the terms. All right. It'd be nice if we had because there's more factors. Like if you write n minus k here, this part agrees, but then you have k terms. You get the first k terms here and the first k terms on the bottom that survive. So I'm claiming we'll get something like this. This is the 0 term. Well, you know, this is the first term, like 1. You get 1. We're going to have k of them. So it's 2n minus 2k plus 2. Like that. And then downstairs, this is 1 term, 2 terms. We're going to have k terms. So this is like a 2k. Maybe potential. As long as you're not quizzing me. What's your question, potential? As you can see, I have major headaches. Welcome in, potential. The last time someone said that, they were just in and out. They said, "Can you help me?" and then they disappeared. They were mostly just spamming. What am I gonna do with this? I mean, they match up except for this thing. If I square it, like I mean, I could take advantage of the fact that this is magically like symmetric. Oh. Well, you could put it in Imgur and like paste a link. I mean, this does not bode well that it's too complicated to type out. So I'm kind of excited that this is symmetric. The only one this is not symmetric. Like A1 is a thing. A1 looks like this. But this is the same as this term. See what I'm saying? I'm surprised I didn't notice it immediately. So when you add like A1 and AN minus 1, you get these things squared. You get Q squared plus this junk squared. Oh, wow. Huh. Well, oops. See, I knew I would regret saying yes. Let's see. All right, I'm looking at it. Log 2 is this, log 3 is this. Number of digits of this ridiculous thing is this, and its leading digit is blank. Well. I don't know off the top of my head. Of course, I haven't really thought about it. Man. I can't see anything. What the hell? Here we go. Oh my god. Everything's falling apart here. All right, here we go. Yeah. Well, you might want to AI it anyway. You don't want to trust me. Obviously, like, what are some things that I know? 6. Log of 6. We can just add these, right? How does this help me? We get 1 times log 6. And we get 0.7781 as the logarithm. So in this situation, like when this is my log, well, I mean, log, oh, you said base 10, didn't you? So I'm already lying. Whatever. Anyway, in this situation, like the integer is probably telling you how many digits, right? If you truncate this, you get 0, so that's supposed to correspond to having less than 10, you know? The fact that this has not reached 1 means we're taking a log of something that's less than 10. If you looked at something like 10 times log 6, which would be 6 to the 10, right? You'll get 10 times this number. Again, sorry, I keep using natural log. I meant log base 10, but whatever. Anyway, if we do it in log base 10, and you multiply by 10, you'll get 7.781. Does that tell me the number of digits? Like if I took log base 10 of 100, you get the number 2, and you know that there's 3 digits there. If you did something slightly smaller, you won't quite get 2, right? If you take log base 10 of like 99, I don't know what it is, but let's say it's not 2, right? So the first thing I'm noticing is if I truncate this and add 1, that'll be the number of digits. So like this is telling me there must be 8 digits in 6 to the 10. As for the leading digit, I mean, can we, I mean, I don't want to just take e to this, right? Like one obvious thing we could do is undo the work that we just did, and that'll get you a big number. That's kind of a problem. I don't know if there must be a clever way that I can like eschew all the lower digits and only get the leading. What if I, well, it's going to be wrong is what it's going to be. I was about to say, like, what if I just chop off all of this? Like, what is e to the 0.7? Anyway, this should give me back 6, right? Ah, damn it, not e. God damn it. 10 raised to this power should give me back 6, right? Let's see if this stupid calculator works. Why does it do this? Man, I hate this calculator. Useless. All right, whatever. That's fine. We'll just do it. Okay, 0.7781. Right, if I took 10 raised to this, well, I can't. So back up. Let's try that again. 10 raised to 0.7781. Well, see, now I can't even trust it because like it rounded, right? Because I wasn't super accurate here. Yeah, so I can explain the number of digits. You see how like 6 to the 10, you'd bring the 10 down, and when you get 10 times this number, and it became 7.781, and I was saying if you truncate that and add 1, you'll get the number of digits. So for our situation, you should get 100 log base 10 of 6 is 100 times this number. That's 77.81, and if you truncate and add 1, you'll get 78 digits in your number. But for the leading coefficient, you're saying it's still 6? Okay. Huh. Well, you did take only powers of 2 and 3, right? You got 2 to the 100 times 3 to the 100 is your number. How does that help me? So, yeah, anyway, did that make sense for the digits thing? Because that part is pretty clear to me quickly, because that's kind of what log does. Like, I knew that I'm really intimately familiar with this, right? Log base 10 of 1,000 gives you 3, and that's like the number of zeros. So that's basically the power of 10 that you're looking at. And that's what you're talking about when you say number of digits is the power of 10. So like when you did log base 10 of something with, I mean, this doesn't actually have k digits. It has k plus 1 digits, but it gives you back k, right? So that's why, like, this kind of thought process is why we're able to get the digits so quickly. Because you're doing log base 10, and when you say digit, you're talking about powers of 10. And that's what log does, is it gives you back the power of 10 that your number is. So that's why that made sense. But the leading coefficient, I'm not sure on that one. I mean, not the coefficient, the leading digit. There must be some clever trick that I can't think of right now. Obviously, it's even. I mean, it's clearly a multiple of both 2 and 3, but that doesn't mean it has to be a... No, wait a minute. I'm thinking of the last digit. Its leading digit is blank. Yeah, why would you know the leading digit? Well, what if it was like 6 squared? Because the leading digit there is 3. Why would I know? Like, let's go ahead and pretend this helps me. 15562. How do I get the leading? We can't, like even this, if I just do, so like the way to undo this is just take 10 raised to this number, right? And that'll give you back your number. It'll give you back this argument. It's supposed to give you 6 squared. It's not. Oh, actually, you know what? Even if you did round this a bit, it'll be pretty accurate for the leading coefficient, for the leading digit. It's that last digit that I was like, oh, it's not going to match up. But yeah, it's okay if this is a little sloppy, because we're still going to be on the right order. Like, your leading digit is still going to be pretty correct. All right. That means, like, what if you took, we were looking at 6 to the 100, right? What if I took 10 raised to, it's going to be some huge number. Damn it. Anyway, what I was about to say is that it should agree with like 10 to the 77 or something. Like whatever the leading digit of this is, it should agree. It should be the same as your leading digit. But that's such a huge number. Like, how is that going to help me? Yeah, look stupid. It's stupid. That doesn't help. It helps here, but it's such a small number that no one cares about that. If I took 10 raised to 1.5562, see, even that was, well, it's wrong in the last digit, but the first digit is correct, you can see, right? But that doesn't help you, because this is such a huge number that, like, if you could do that, you would just take this, you know, if you could do this, you wouldn't. Anyway, all I've been able to tell you so far is that the leading digit should coincide with this guy as well. I didn't bother to round it or anything, because it shouldn't. Well, the good news is you didn't really need a calculator for this part, for part A, or for part 1. Because if you just multiply this by 100, you'll get roughly 78. I should say, no, you'll get 77.8. and then you want to truncate and add 1. I didn't actually round it. I went down to the nearest integer below, like I took the floor function of this, and then I added 1. I didn't round. I'm sure, well, yeah, I don't want you to think that I rounded. But anyway, and this was kind of based on, I thought of that so quick because I was thinking of this stuff, base 10, log base 10 of various powers of 10 just it basically spits out the number of digits. It's always off by 1, so you just have to add 1 to correct it. So this was the clever idea for counting the digits. But the leading digit, sorry, I can't think of anything right away. My only thought was that, like, say we're dealing with a smaller thing like log of 6 squared, or let's even do log of 6 cubed, right? We can do that pretty quick with the number you gave me. We could just triple this. If you don't let me use a calculator, this is something like 2.12, I don't know, I give up. 0.7781 times 3. I'm sure we could do that by hand if we had to. But I get this, right? And so what I was going to say is this is the number in base 10. Like if you took 10 raised to this power, it should give you back 6 cubed. Right? So if you were able to get this number, which I don't know how you're going to do without a calculator, but if you were able to get this number, they would, like, the last digit might be wrong because this is a little bit off, this 2.3343 number, like, because this is not exactly, what you gave me is not exactly log 6. But anyway, if you were able to compute this number, the leading digits of all of those are going to agree. Like, I don't know what 6 cubed is right now, but I'm betting you that, damn it, I did it again. 10 raised to 2.3343. I'm betting this is extremely close to 6 cubed. When I did this out, I got 215. And 6 cubed is, I don't know, 6 times 6 times 6. Damn, I'm way off. Well, I fucked that up. Sorry. Well, that was a terrible idea, Dave. Why did that fail? 6 cubed. 6 cubed is 10 to this. There's no way that this was wrong. Did I multiply wrong? Okay, I multiplied wrong. Good. Yes, this is 216. I was going to say, that doesn't make a lot of sense that it'd be 390. So yeah, see how close that is? So like that's the only other thought process that I have. So you could tell him, well, no. You could tell him that the leading digit agrees with this. That's like something that I know just innately. Because I'm undoing, we took a logarithm and now I'm undoing it. So I know that I'm going to get the same number back. So like in your example, if you took 10 to the, well, yeah, even 77 should do it. These have the same leading digit. I don't know if he told you some sort of trick. Wait a minute, this doesn't make sense. Because I'm getting 1. This can't be right. You need this decimal here. All right, fine. So anyway, I guess I'm saying if you were able to compute this, it'll obviously give you back 6 to the 100. But that's kind of a useless statement because, first of all, it's a huge number. Don't do what I was saying over here. You can't truncate it and take a power of like 10 to that power because it's just going to give you 1 out front. 10 to the 8-1 is da-da-da-da-da. Huh. That's interesting. I'll have to check out what you're saying a little later. Yeah, that's pretty cool. Some numerical analysis thing you're talking about. I'm not familiar with what you're saying right now, but it sounds like you're It sounds like you're saying you can just focus on the fractional part, and that'll get you the leading. That actually makes some sense, right? Because I was saying the integer part's not going to help you. That's really interesting. But that's the first digit, not the last digit? No, first digit is what you were after. Huh, okay, interesting. Yeah, I like it, man. So yeah, 10. You're saying if I just take 0.81. Yeah, that's really clever. I wasn't really familiar with that, but that makes sense. Damn it, I did it again. I keep doing this. All right, 10 raised to 0.81. You're saying that gives me... Huh, yeah, why is that? Why does that work? Because this is a sum. If I took 10 to like n plus d, here's the... Here's a part that we know is just a giant number with a leading 1. And then you're scaling it by... Yeah. This is what you're saying. That's pretty clever. So your number looks like this. And you know that this is the part that controls the leading digit. That's really clever. I just wasn't familiar with that. It seems like some basic, right? It probably comes from chapter 1 in some numerical analysis or numerical methods type book. Yeah, did you see what I just said there? That's explaining why your mantis trick just worked. So the n here obviously is the integer part out front that we're trying to ignore because I can't possibly take 10 to the 77. It wouldn't help me anyway because it's just going to be a 77 zeros. But yeah, this is for sure what he wanted you to say as an explanation. Is that this is how exponents behave. So all you need to do is compute the fractional part, and that's going to give you, the interesting part of the number. This is in effect giving you the magnitude or like the number of digits. But this is giving you more discrete, like more specific information about the number. That's a neat question potential. I'm going to take a break real quick. I need a beverage. Need some water. I'll be back. But yeah, potential simulation. I hope this part made sense because you just inspired me to jot this down and do 10 to the fractional part, and that's pretty much exactly your answer, What's going on? Hey. I don't know how to pronounce this. Endlib alibide. All right, world. Let's see if I can do something with this again. I'm noticing that it's symmetric. Maybe that helps me. These are not symmetric. Like, these guys are neighboring. And I have to sum over all of them. That kind of sucks. And like even Cn minus 1, for instance, it's going to be, well, here. It would be, I want to say A0, well, it'll be An minus 1 times A1 plus plus An, let's see. At 0, you get a bunch of things that don't make any sense. Finally, at n minus 1, you get n minus 1 and 0. Yeah, so for instance, Cn minus 1, you would get a n minus 1 against 0. Yep. Plus an against 1. We got a formula for an, and damn it, a1 is nasty, unfortunately. A0 is 1, and I guess we have a formula for an minus 1. It looks very similar to a1. It's just that this leading power is different. So that makes me think we were able to confirm Cn. If we look at Cn minus 1, I'm claiming that it's now, that's a 1. And these two are very similar. An is what? Actually, An is Cn, is q to the n squared. Yep. Okay. So this is An minus 1 that looks like this. And then the n minus 1 term gives you the same thing that a1 would give you. It's basically just a single term. Oh, we just wrote it down. It's right here. 1 minus q to the 2n over 1 minus q squared times 1 plus an is this guy, q to the n squared. And then a1 is q, and then this term again. So they have the same denominator. Upstairs you get q to the n squared plus 1. Gross. I don't think we should expand this or anything. I'm just noticing we get this plus q to the n squared plus 1, right? And that's times this stuff that they have in common. So this is the coefficient for Cn minus 1. Do you think I'd be able to handle this guy? It doesn't look very nice. Is it going to pass off in any way? Well, you know, the last one is nice. And then they're symmetric. You know, then they look like this, more or less, except that there's more terms here. There's more factors on that chunk. So you do get a series of things from 1 to half n that look like this. That's basically what this form is going to be. But the problem is you're adding them separately, and each time you add them, this thing that's next to them has an extra factor. Yeah, that's not going to be it's not going to be pleasant to try and add. Maybe I should try to move on so we can like eventually finish 50, 53 and 54 and stuff. Was not super successful. I got a better grip on what my formulas are. But if we put this guy next to another product, if we took the formula like AK minus M, we try to come up with a general formula for that and then sum over it, I don't know. I'm having kind of a hard time. It could be done. And that's not really what he did. So I'm sure he would have recognized that you could do that, but what he did was he gets this recurrence relation, which I had also gotten, and I guess I verified this separately for my case. So he basically just uses this to solve for CV. I guess that makes sense though, right? The Q's are just odd Q's, that's how you get that part. And yeah, so his formula is actually kind of similar to what I did for my formula. It's just a product. I'm sure if we, so like divide by this, you get 1 minus Q to some even power. That's where those are coming from. I'm not sure why he got 2n minus 2k. That's agreeing with that. So did he divide the other way? That doesn't make sense. Yeah, why would he have these on top? I would think it would be the reciprocal of this. You obviously want this on top. So like if you start at 0, you get 2n, which is not even in his list, by the way. And then, when k is 1, you get 2n minus 2. Again, not in his list. It's almost obvious that this is the numerator and this is the denominator, right? But somehow this ends up in the numerator. Although, I'm assuming that we have a grip on C0. Like, in my case, A0 was 1, but I don't know what C0 is. If I had that, maybe that explains, I don't know, man. Because I didn't even want to do this computation of C0 out. But maybe that helps explain how he got this. All right, if we believe him, in fact, I'm going to leave my stuff. This is 52. This is 52B. And this is 52A. I'm just going to use a separate sheet for this. So yeah, if we believe him, that you get something like this. CK plus 1 is CK times, and then he has an odd power times 1 minus Q to the 2n minus 2k, and he's dividing by 1 minus Q to the 2n plus 2k minus, nope, plus 2. That's his recursive relation. Also, he points out somehow he got this. But anyway, if k is less than n, you get this formula. Yeah, so what I was going to say is, suppose we knew C0. Actually, he's claiming C0 is what? Just, well, we believe this formula. How would that help me? How am I supposed to plug in 0? I still need to know C0. But whatever, some number. Oh, do you know Mina? Mina disappeared on us, I think. Hey, Mina followed me. Thanks for the follow, Mina. Yoink. Consider yourself followed. You're just excitable. Stucky is a very excitable person. Yeah, so I know C0 is something. Man, it's frustrating. C0 is what you would get if you could plug 0 into that damn function. Oh, cool. That's awesome. Right. Also true. See, I should be reading your article instead of doing this BS. I would be learning a lot more. This is kind of just torture. And I have a feeling the next couple problems are going to be more of the same. And what do I get for this? Just credit or something? Do I get... Yeah, I don't know. Do I get street cred for pushing some symbols around? I already know how to do algebra. Anyway, so for instance, C1 is C0 times, then you just plug in a bunch of zeros. So you get Q, 1 minus Q to the 2n, 1 minus Q to the 2n plus 2. If you do it again, you get C0 along with this junk. But now you also get Q cubed times 1 minus Q to the 2n minus 2. Yeah. And then downstairs we get this puppy and another one. Etc. So in general, you get C naught times the Q's add up to be, let's see, this was 2 squared, so you'll get V squared, and then you'll get a bunch of junk of this form, stopping after, in this case it was 2 factors. In our case, we'll have V factors. So if this was the first, well, the 0th, here we'll have V minus 1. Does that make sense? At 2, we get 2 times 1 over there, yep. Or 2 minus 2V plus 2. And then downstairs we get Q to the 2n plus 2. 1 minus Q to the 2n plus... again, it's like... Well, this time was 2 times 2. This was 2 times 1, 2 times 2, so we're getting 2 times V. That's a nice general formula, and it supposedly agrees with what he said was this stuff. Yeah, it really doesn't agree with that, does it? No, it does not. This part agrees. Upstairs doesn't look like that at all. No, no, no. No, it does not. Here, I'll, here's my notes. There we go. Here it is. If you want to see how it really does not resemble what it's supposed to. So this is what I would have gotten. Somehow the C naught term turns this into that. I'm not getting that, but that's weird, wild stuff. I don't see how that's possible, frankly. Well, I mean, it's possible. But mine starts at 2n and decreases. I mean, mine numerator looks like his denominator. I don't get what's going on, man. I don't get it. This problem is kicking my ass. It's not even that hard. All right, whatever. You know what? Maybe we should admit defeat on this set of problems. Because like 53, he basically says, take the limit as n goes to infinity. And then when you look for an explanation, he's like, yep, do that. Do what I said. Take the limit. Just do what I said, man. Deduce the following by taking the limit. And again, like, I don't get this. I get this. I don't get that term. I would have thought that that term was in the denominator. Over here? It's very confusing. And what happened to all the reciprocals? Oh, never mind. They're still there. Good. So this is almost like... Yeah, I don't really get it. This shit is crazy. And I can't even use my explanation because mine sort of gets worse. This is what I had. Oh, I was trying to work through. Yeah, this was. I started doing his method. So I took his relation, and I would have gotten this. I don't know how he got his formula. And if we do it my way, we run into bigger problems because I have to sum over a bunch of products. So I have to basically take this and multiply it by like a shifted version of the same formula, and then sum over all that junk. What am I going to do? Like, suppose I believe him on 52. He gets these... Shouldn't this be the coefficient in front of, you know, when we look at series 53, this right-hand side, he is ignoring everything that was in front of it, right? He's only using this part of it. And somehow all this stuff, he's like, oh yeah, that doesn't matter. Like, clearly he's multiplying sort of by this part, right? That's how you ended up with that term. But then what? Then what? You have this junk upstairs times q to the k squared. So like what? What am I supposed to do with that? But then at least, well, then the left-hand side does look like the same function we'll be dealing. That part is the function. This part is maybe the denominator of the coefficients, right? But then, why would I get this? These things don't just go away. Huh. Alright, so it looks like 55 is also a special case of 53. 56 is going to be 53. 57 is a fresh problem. And that's it. And then we're out of the woods. The rest of them don't have to do with this. So that's what I thought yesterday too. 57 looks like a new problem. It's really like these guys. 52 through 56 are all the same topic. This nightmare function. I wish I understood it. I'm kind of close. You can see I kind of circled around it, but I got a worse formulation of the answer. And I can't really even make sense of his answer. But he didn't say anything particularly challenging. And I got this far. I got these relations. I just don't quite get this. It's almost like I got it upside down. Am I just being an idiot? Did I just read it wrong? This is in the denominator. 1 minus q to the 2n. Minus qn minus 2v. Wait a minute. Why isn't this minus? Did I write it upside down? You dick. Wait a minute. No, I didn't. I did not write it upside down. Ah, I hate you, Pólya. I hate you. I didn't write it upside down. This is what I'm looking at. If you divide by this 1 minus q to the 2n whatever, you get that. We're going from here to there. So it was this times this, divided by 1 minus q to the 2n plus 2v plus 2. This identity follows blah. And I agreed with that. Like yesterday, I did it out and I got the same thing. So I can't really argue with these two parts. Which gives me this. Anyway, minus q squared. It's almost like he gets the same thing, but upside down. Alright, maybe I should bail. I'm clearly going to have to spend more time on those. So, in the interest of actually making progress, I'm going to skip ahead to 57. Just so we don't get bogged down on this for days. This is, again, 52, but we're doing it his way. And If I ever make any sense of that, I'll come back and make a comment about it. By comment, I mean like a 1 or 2 hour long discussion explaining what on earth happened. Let's move on. 57. Q is a fraction. G of z is this series. Looks like you get 1 minus z initially, but then you get 1 minus z times 1 minus qz, q squared z, etc. for the rest of the terms. Oh, thank God. All I have to show is that it satisfies this functional equation. Thank you, Lord. Wow. Looks kind of rough. That's weird. There's 3 terms on the left, and then you got your product. All right, we'll see. We'll see. Let's see if I can write it down. So I'm looking at 57. I had to admit defeat on 52 and its cousins. 57 says, for q less than 1, define g as, here's the first term, oh, it's not quite square. It's q square over 1 minus q square. That's interesting. And then you get 1 minus z, then you get 1 minus qz. And the third term is q cubed over 1 minus q cubed, 1 minus z, 1 minus qz, and 1 minus q squared z. Okay. Etc. Anyway, thankfully, all we have to do is show that it satisfies this functional equation. The product, the infinite product of these guys, the q. So 1 minus qz, 1 minus q square z, 1 minus q cubed z, etc. Huh, we'll see if I'm feeling so happy about that in a minute. This is bad news, my friend. Bad, bad news. Well, so when you throw qz into this mess, you can see this guy matches up with that, but this one becomes, nope, it doesn't get squared. It's actually, this coincides sort of with that, but it's missing, okay. If we put a qz there, I can kind of see that it's missing 1 minus z, right? But I can't quite get it back. It like shifts everything. So that's frustrating. If we took 1 plus this stuff and subtracted that, you would get, all right, we can at least write that down. So the left-hand side, we'll just jot it down, I guess. There's got to be a faster way to write this. Yeah, you get the idea. And then we're subtracting. When you hit this with qz, the first time it looks familiar is right here. Oh man, you only get q squared. That sucks. We get q squared over 1 minus q. That's very weird. And then at qz you get 1 minus qz. Minus q cubed over 1 minus q squared. And then we did have 2 terms there. Now those terms look like this. They're missing, notably, 1 minus z. So I can't just like, here, I should have written this one down. So I can't just like subtract them like I was just hoping to. Because they're missing 1 minus z. Although, if I distribute the 1, right? So the first term you see when you do qz in the function is this guy right here, okay? I'm noticing what? If you forget about the z for a moment, when you do 1 times this and that, it almost matches up. The denominator is wrong, but... And by the way, it's supposed to be this product on the right. Does that seem like a worthwhile thing to do? On the right, I'm not sure how I'm gonna... I guess I could get a formula for like a finite version of this and then try to take a limit. It's probably easier said than done. Alright, so we have this, then we get itself minus q squared times it. Oh, I see. Minus q squared z, wait a minute, that's... So we get these two terms, then we get a squared and a cubed. The squared is just a single z, but the cubed suddenly has z squared in it. It's probably a nice way. Huh. It's not quite geometric, right? Because this is not, that stupid z is not also to the power. So it's not like I can just write this as 1 plus qz squared plus qz cubed, etc. Huh. So when do the powers change? Only on the last. So like here, when you do q cubed z times the stuff, the only time you get a higher power of z is on the last term. We're getting like q to the 6 z cubed finally. Yikes. I've got minus z times that stuff. So I noticed that I could at least get those terms, these nasty terms, by like distributing, but I'm also getting minus z times that term. Of course, this is off, but that's all right. We can, I don't know what we can do about that. So like, here's the stuff out front. If you just start distributing, you get, I'm ignoring the z, the minus z. I'll write that in a minute. Right? Now, we're also subtracting this stuff, like this matches up with that. This is the first time you start subtracting, is you've got this term. Unfortunately, the denominator is not the same. But everything, the numerator actually is the same. So that's cute. Yep, two terms there, right? The denominator changes again, 1 minus q squared. So we can group these terms. All right, so I'll do that on the next line. But also don't forget we had minus z times this, minus z times this. You know, it'd be easier to just write minus z times but that's all right. All right, so what? Well, if we group these guys, we still have this mess to deal with, but we could at least plus this, plus 1 minus z times that? That's weird. I wonder why that happened. I guess I'm just noticing that this guy didn't get touched. But all right, 1 plus that minus itself. So like that 1 plus 1 minus z. Yeah, this first one didn't involve anything. It's just extra. Then if I break them apart, I can sort of regroup, but I don't know if that's going to help me. So, and then what? Then you get all this junk too. And that's just your left-hand side. What am I going to do with these z's? I don't know. We'll see. So we got 1 plus q over 1 minus q, 1 minus z, right? Minus z times this original stuff. Well, all right. We got rid of this one already. So we'll do the case of q squared, 1 minus qz. Oops, damn it, that's not what I meant to do. Plus q cubed over 1 minus q cubed, 1 minus qz, 1 minus q squared z. Yep, that's right. We can keep going if you want. q4, 1 minus q4. Now you've got 3 terms, 3 factors. Etc. Right? And then we got the stuff that I just did a minute ago. We can like regroup them, but I don't think that's going to actually help me. But yeah, you get stuff that looks like Actually, let's just add it. You get you know, this minus that, etc., all the way down. So you get, for instance, q squared 1 minus qz. It happens here with this denominator, and then you subtract it with a different denominator. Sadly, it's not going to be some sort of telescoping thing. It kind of looks telescoping. But because the numerators are all different, I don't really anticipate that helping me. So this one's got a denominator of 3 and then 2. Okay. We'll do one more. Anyway, if you did add these fractions, I guess you get stuff that is not very nice, right? 1 minus q minus 1 minus q squared. So you get q squared minus q. Huh. And here you get like q cubed minus q squared. So I could factor q out here, q squared out here, q cubed out here, and you're getting odd powers of q. If you do factor, you get q minus 1. Here you get q minus 1. Huh. And the denominator becomes a product of these. Product. That doesn't cancel or anything. I'm just noticing we're getting odd power of q times 1 minus q minus 1, which is a pretty nice form, I suppose. Nope. Didn't really recognize it. I still have this minus z times all this junk to deal with too. I mean, we can write down what I was thinking, but I still don't see where we're going from there. So we can do that next line if you want. But I don't see it doing much. I just noticed there would be a pattern in this part that looks like it might telescope. But then I'm just going to have these in the denominator when you add these fractions. So all I'm doing is adding the fractions. And you do get sort of a nice pattern, but I don't know how it's going to help me. And Actually, does the first one fit the same mold? Maybe, kinda. Not really. Well, I guess we'll see when I write it down. 1 plus q over 1 minus q, 1 minus z times all these crazy terms. It's a crazy term, and that's a crazy term. All these crazy terms that make you want to die. Da 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 da. And then more stuff. More stuff. So I had said, 1 minus q minus 1 minus q squared. The ones cancel, you get q squared minus q. And very similarly for everything else. This is 1 minus q squared minus 1 minus q cubed. That's q cubed minus q squared divided by the product. So knowing that this is q squared minus q, you could factor a q out, and you'll get, well, when you factor out all of these, say you have q cubed minus q squared, when you factor q squared out, you get q minus 1. You always get q minus 1 up there. So the numerator is now about to look like q cubed, q minus 1, and then you get the factor. And then downstairs you have the products. Interesting. Something magic might happen there. The next term, we get q squared is what we're factoring, so you get q to the 5. Again, times q minus 1. This time we have 2 factors. Downstairs you get this product. For this one, you get q to the 4 minus q cubed. You factor q cubed out, you get q to the 7. Of course, you get q minus 1 again. Now you have... Did I mess this up? Damn it, that's not there. Wait. Oh, no, I see. Good. So yeah, we got 3 terms this time. 1 minus qz, 1 minus q squared z, 1 minus q cubed z, and this denominator. And obviously it continues. We got our new denominator. Yeah, baby. So what? How does this help anyone? And I guess also kind of curiously, does this first one fit the same mold? It is an odd power of q, but the bottom, I guess it's a 1. 1 minus q to the 0. Eesh, you can't do that. Yeah. Is it q? It just doesn't quite fit, right? I was hoping to group this with them for some reason. Q. Nah. Like q with no powers of this. What if I multiply and divide by q minus 1? You get something stupid downstairs. It's not going to look like this. Huh. Alright. Well, anyway. So yeah, this is still my left-hand side. And I'm stuck. So of course, for every one of them... Oh no, you don't. I was going to say this cancels every time, but we could factor it. We could make it cancel. Like if we factor 1 minus q out of this, we get 1 plus q plus up to q cubed. So for instance, like here you get 1 plus q downstairs when you factor there. Of course, we're going to have extra factors. We could leave the bigger one, I guess. Get 1 plus q. Huh. Yeah, I don't know. And then if you did expand the right-hand side, we get 4 terms, we get 8 terms, you know. Eesh. Hey, wait a minute. We've done something like this before. Well, whatever. Boo. Boo. No. So we could jot down like a formula for what the kth term will be. Oh, was it the last one? Yeah. So obviously we do it again and we get 16 terms and 32 terms. So stuff that involves z is actually, I mean, it always has a negative sign initially, and it's a power of q. We don't start seeing z squared stuff until q3. because it's the first time we encounter it here. For z cubed, the first time you'll see it is on q to the 6, I guess. Yep, right there. So you can see what's in front of z is like 1 minus q squared minus q cubed. It continues like that. You see a bunch of those. The squares is similar behavior because you're just multiplying this term against that same stuff I just described. But it doesn't actually begin until right here. So the leading coefficient on the z squareds is like, well, here's the problem though, I guess. So here I got like 3, I got a 4, I got a 5. We're about to hit it with negative q to the 4 against this. So you're actually adding q to the 5 z squared. So you're going to get 2 of these. So the terms are starting to combine. I wonder if I can get like a closed form thing for this. Probably not, right? I mean, like for this, just a finite version. That's what we're talking about. Yeah, I don't see how you're going to. So I did out 1, 2, 3, right? I didn't bother to simplify it. But for instance, the q's obviously on that largest power, you can see that they're the sum of the numbers, right? q1, q2, q3 is just the sum of those exponents. So there's a formula for that term. What about the z term? I mean, I know that here we just had a sum of both, right? The cross terms. You're always going to get that. But that's just the first order. Like z to the 1, I know we're going to have minus q squared, minus q cubed. It goes all the way up. So I guess what's confusing me is maybe the z squared terms, and I've got the highest term. Well, it shouldn't be that impossible, right? If I had a... No, I gave up on 52. Decided to move on. And actually, where are we here? Because I knew it, so it was 52 is the one. I mean, it doesn't even look that scary, but I was able, so in his answer, I was able to confirm this part off stream. So I talked about it in the first hour, but I didn't really like rederive it. So I was able to confirm this part, but then I can't quite get here. It's like I have the reciprocal of this, but I also don't know what C0 is. I mean, he says it's just given, I don't know. Doesn't make a lot of sense. And I can't plug in like z equal 0 into this function because of the reciprocal. So I don't know what C0 is supposed to be. And if I knew that, I would get a nice closed form thing, but he's saying the closed form is this. So I got the Q part, but I don't know, I couldn't quite work it out. And anyway, then if you look, like 53 uses 52, 54 uses 53, 55, 56, they both refer to 53. So so I skipped these 4 problems, sadly, because I'm going to try to do 53 for a minute, and his hint is useless. He just says, use 52 and take the limit. And then in the answer, he just says, yep, take the limit. So, I mean, it looks like he's referring to a much later problem too, but that's not going to help me. So yeah, I couldn't quite make 53 work, so I just bailed on the next chunk. I started looking at 57. So 57, at least I thought I was happy because it's just show that it satisfies this functional equation. But it turns out that this is pretty gory. So I'm looking at 57 now. But it's not, it's also pretty nasty. So like right now, I was trying to see if I have a formula for the right-hand side. My left-hand side, I also don't have a very nice formulation of it. This is my work on the left-hand side. So this is the problem. I'm trying to show this. The left-hand side, if you just write out 1 plus g, and then subtract g at qz. So you get qz there, you get qz, q squared z, and these powers have increased. So then I thought, well, they look kind of similar to these, so I'll group them together, and then we got like a difference like this, and then I added those fractions. I ended up with this mess that is probably illegible. But so on the left-hand side, I get some stuff with a minus z times some stuff that I don't really see how that's going to clean up. And then you get odd powers of q against q minus 1, like more and more factors. So I know that I could cancel one of those q minus 1s every time, but I don't quite see that helping me out yet. There's 2 factors of 1 minus q downstairs all the time. Anyway, that's the left-hand side. This mess is what I have for the left-hand side. And then I started looking at the right-hand side. There's a pattern here, and obviously all we're doing is multiplying by this factor each time. So once I get, like, if I had a sense of a formula, we could probably prove it immediately with induction. But yeah, I didn't immediately see what that would be. If I group these terms, like z squared, you get cubed, quarticed, quadrupled, and quintupled. Cubed, quadrupled, quintupled. So you sum those. I don't know, man. Like, if you were to stop at n, I can see we got like 1 minus z times and it stops at, I guess, n, right? So here we did it twice, we got 2 terms. Here we did it 3 times, we get the 3rd term. For z squared, I don't know, something similar, but it doesn't start until Q3. So like the first time that occurred was this second step. So the leading coefficient on that is Q3. But other than that, you kind of have a very similar pattern because they come about in the same way. It's just negative Q3z times the stuff, or negative Q4z times the stuff. So is it something like plus z squared q cubed plus q to the 4 plus, I had q to the 5 because I stopped at n equal 3 or something. Is this n equal 1? Yeah. N equal 2, you only get this term. N equal 3, this is the last term you get. So it's something like q to the I was going to say n plus 1, but that's wrong. Damn it. So q cubed, q3, q4, q5. Actually, as we went from here to there, you got 2 more terms that were squared, because we started out with like 3 terms that were z. So however many are here, on the next iteration, you get sort of that many. Huh. Not seeing it. Is it like 2n minus 1 maybe? So on 1, we get we just get q cubed. So maybe I should do 2n plus 1. Although I thought this was the 1 case right here. Yep, 1 case. Okay. So on the 2 case is the first time you see anything here. And it gives you n plus 1. Or really, oh yeah, is it? Yeah, it does. Wait, does it? Well, it will on the next round. It'll definitely have 2, but at this stage, see, if only I was any good at combinatorics. I don't know why I was trying to like deduce a formula just from taking 3 steps, but yeah, the first one comes about. Anyway, the next one, you're hitting q cubed z against this stuff. So all the z's you get are 3 plus 1, 3 plus 2. So are those the only, oh yeah, and this guy against 1. So 3 and 4 and 5. That's how I got those. And they happen to all be positive. So like the next time around, you will get the same ones that you have, of course, from the 1. They'll still be positive. And then you get negative q to the 4 times the linear guys, these guys. So it's q to the 5, 6, 7. I guess that's it at this stage. So we got one term, then we got two more terms, then we got three more terms. So it's growing linearly. But I'm just burnt out. You get n more terms each time. So here we had none, we finally get one, it begins at q cubed. On the next level you get two more terms, but I was hoping for just a nice yeah. I was hoping I could just jot it down, but that's not really how it grows, huh? It's like 1 plus 2 more plus 3 more. I mean, that kind of implies it would be this, right? n plus 1 over 2. Is that accurate? At 2 you'd get 3 terms, which is correct. Of course, the size is wrong, right? What if we took... Anyway, I'm saying, what if it was this? Why would you think it's that? I'm just adding up the terms? That's weird. That's weird to do. That's how many terms you'll have, but that's not going to dictate what this is. For some reason I was hoping it would be like this. Or actually, that's not what I mean. I mean this minus 2. What? Okay, you're just confused. I mean, it's obvious that's what's happening, but anyway, not sure why I'm trying to do that anyway. Oh, yeah. Yeah. You're saying, like, this one would be... Could be. So on the first time around, you don't see it until you hit 2, right? And then you get 2 times 1. Yeah, I don't quite see it. Is it that maybe minus 1? Because the next time around I'll get like, yeesh. Yeah. Anyway, I shouldn't be doing it this way anyway. I was hoping to just guess at a formula and then prove it, but... this weird product, as soon as I wrote it down, I was like, oh no. Because we were just doing, those were the problems I just skipped, were like showing that that's equal to some series. It like looks very reminiscent of the junk that I just skipped. It's not the same, but it's also like, it's close enough to be like, wow, I mean, I wish I knew what was going on here. Maybe that machinery would help me. All right, so if we just cheat on 57 to see what he's doing, what? Letting an be v's, you get this formula. What the hell are you talking about? Oh, sure. Okay, sure. Minus q to the n. I should really put the problem up in the corner so you have any clue what is going on, but I I need to make a habit of doing that. Because otherwise, this is just impossible to follow what the hell I'm talking about. But yeah, this was our left-hand side. It looks like he's actually, this is the definition of G. Wait, what happened to the, oh, okay, he added it in. I'm a little confused on that. He put a Z there. Yeah, this is messing with my brain, but I guess that's plausible. Yeah, this one's kind of a dirty trick, huh? It looks like he just immediately rewrote the left-hand side as a single sum. And then he said, I'm going to replace like these negative q, these powers, negative q and z, negative q to the k to the z, or times z with like ak. And so then we're looking at like 1 plus a1, or sorry, yeah, 1 plus a1, 1 plus a2, 1 plus a3, all the way up to 1 plus a n minus 1. 1, 2, a3, huh. And then he fidgets with it and gets it to apparently equal the right-hand side. I don't, what? Okay. Did he just do it one at a time? Like, so here there's none, and then he says, oh, that's 1 plus a times this. That's 1 plus a times 1 plus a2 plus a3 plus a... Oh my god, my brain. He sees this. Yeah, yeah, right. Telescopy. Distributivity. The telescopy distributive law. Well, it's better than what I was doing. It's always cute when I see like Gauss. Gauss is the reference. Oh yeah, Gauss did this in 1863. Obviously you can do it, right? It's been like hundreds of years. Here's Euler. Wait a minute. Euler is being referenced? Volume, published in 1915. Okay. I was going to say, how did Gauss publish this in 1863? Is it opera? I don't know who these people are. Opera Volume 2, Bob. Maybe it was republished? Boggle. All right. 57. Yeah, distributivity. Indeed. One plus 1 plus a1. Is that first? Is that 1 plus a2 is that, etc. telescopy. All right. My brain. I was trying to get. I guess I was trying to shed some light on 52, but that is not how the stream went. This reminds me of something. John Stuart Mill. It's kind of not how the phrase goes. There it is. There it is. I got AI. Yeah, I don't know. So that's where we are today. I think I'm going to wrap up the stream. Today I'm a guy who cannot do the problem. Yeah. Well, no, I knew I had it wrong. I roughly knew it, but then I Googled it and this first thing came up. And I was like, that doesn't sound like what he said, but close enough. I think, let's see. Yeah, I can't find it right now. But Keith Conrad had this in a paper, or like his teaching statement or something. I forget. I learned this quote from all right, I must admit defeat for the day. Feeling a little sad and overwhelmed. The annoying thing too is like, even if I figured out 52, I'm not going to get these next couple right away. And they don't even help with 57. That's just a totally separate issue. But that's all right. 57 has an answer that makes sense. We can churn through 57. And 52, despite having an answer, I guess if I understood it much better, do you think 53 would just pop out? Because he acts like it's easy. He's just like, yeah, take the limit in 52. But to me, when I saw it, I was like, I can't just like this left-hand product, yeah, that's 52. And this is part of the denominator. But there's other stuff going on. I can't just multiply by the denominator and be like, boom, we get part of the numerator. Oh, maybe in the limit, this stuff goes away? like as n goes to infinity, these numerators just somehow, I don't see it happening. I don't see it going away. Yeah, very strange. I'm missing details here. It's also getting to be too unwieldy for Chat GPT to help me. I mean, I guess I could try, but I don't think it's gonna know. Do they? Yeah, they. Well, okay. Like here were his. These are his terms. Yeah. Yeah, and Q is shrinking. Yeah, that goes to 0. Yeah. All right. I guess. Like we get these terms. These are the terms that we'd be sort of multiplying by. So they end up on the left-hand side under that big product. And I was like, well, yeah, I see this is there, but what about all this junk? Because our right-hand side, I thought our right-hand side would be like these. I mean, these. It actually goes from negative n to n. Well, yeah, sure. You could write it like this if you want. Or you could just, since it's even, you can just do z to the v plus z to the negative v. But anyway, yeah, as n gets large, these tend to 1, or to 1, but no, maybe you're right. Maybe it's that simple. Maybe you're right. Because every one of these has a 2n in them. They're all 2n and larger. They stop at 4n, but so what? So yeah, you're right. This shrinks to 0. I can't argue with that logic. And downstairs, it's not exactly the same. Downstairs, they start at q squared, q4. There are a bunch of even powers. It doesn't really stop. But that's the stuff that ends up on the left-hand side. So maybe that's 53? Yeah, I guess you're right. Maybe it's not so bad. Yeah, downstairs we don't get rid of those. We actually multiply by those somehow, and they end up on the left. So if you if you buy that that this coefficient somehow becomes like 1 over this infinite product, that's okay. That's not so bad. Yay! Yeah, exactly. What a terrifying and joyful result. So that's why he didn't explain anything on 53. Because that's the function we were just looking at. These guys pop up in the denominator starting at n equal 1 and just going on forever. And then you get this. It's all right, 53, I'll buy that. 53 follows from 52. 54. Oh yeah, I didn't know what he meant by this. So he's letting z be negative half, or negative square root of q. Okay, in that part maybe? Negative square root 2, so you get q to the n over 2. I don't know. Oh, and the negative alternates. Okay, sure. All right. And then he wrote this, which I didn't understand. Of course, you haven't seen the problem, but yeah. His new problem was 1 minus q to the n. Oops, sorry. There you go. And he says something almost like, so if we believe 53, which was like this product of, well, I lost track of it. Let's jump back. 1 minus, yeah, right. Odd power, wait, what? Plus? Oh, sorry, plus, yeah, plus. 2n minus 1 z to the negative 1, and then times 1 minus q to the 2n, and it equals these guys. Right. So this is 53. This 54, the question is, what's the product of 1 minus q to the n? And he wants us to show that it's alternating, and you get q to the 3n squared plus n over 2. Yeah, that's it. But his answer was, let z be negative q to the half. And then he writes something like, q divides q to the 3 halves. I don't know what this symbol is supposed to mean in this context. Q slash q to the 3 halves. Maybe replace q with q to the 3? I don't know. I guess it would still be less than 1. Q slash q to the 3 halves. This is a magical statement. So yeah, I can see if we let z be this, we get the alternating business, and we even get q to the n over 2. And then over here, do these somehow cancel? I'm not seeing that. So over here, in the previous result, you'd get 1 minus yikes. Anyway, 2n minus half plus half, right? Or minus 1 plus half. So it's like 2n minus half. A little strange. Oh, plus. I don't know why I keep doing that. And then here you get 1 plus... Well, it's the reciprocal now. Oh, that's why I wrote minus. Sorry. This really is a minus this time. For once, it's actually a minus. And then here, I guess it would also be a minus. Like, if you take 1 over... I mean, I don't know. It's negative q to the negative half. What do you want me to say? So here it's... Let's just try this again. It's 1 minus q to the 2n minus half, because we've added half to that. And then for this other one, though, we get 1 minus, this time we're sort of subtracting half from it. So you get q to the 2n minus 3 halves, say. And then we got this stuff that doesn't actually depend on z. And I would from 53, we would know that this is the sum of q to the n squared plus half. I'm getting plus n over 2. And there's an alternating bit as well. So all I did was substitute z into the 53. So he obviously did something here as well. Like if we replace q with q to the 3 halves, does that suddenly... I don't see that working out for me. It's supposed to be just this. Also, there's supposed to be a 3 halves here. So yeah, replace q with q to the 3 halves. That'll get you part of the right-hand side. That'll get you the whole right-hand side. But over here, I'm running out of paper. Yeah, maybe it does work. Maybe it just works. It sounds like he's saying replace, like this symbol, maybe he meant replace q with q to the 3 halves. Because that works on the right-hand side. But on the left-hand side, I don't know how it's going to help me out. On the left-hand side, we have... So let's start with what we have before I do the z part. Instead of q, what the? I don't know, things are exploding in my room. Instead of q, we have q to the 3 halves, which is still less than 1. So it still satisfies the hypothesis for this statement. And then you raise it to the 2n minus 1, which I guess just does that, right? We still got a z there. And then for the next part, we do the same thing, but with a reciprocal z. Don't really seeing this helping us. And then this is 1 minus q to the 2n, but again, it's 3 halves 2n. So it's like 3n, right? And on the right-hand side, instead of n squared, you get q to the 3 halves to the n squared. Times z to the n. So now in this mess, you let z be negative q to the n. Oh, sorry, half. And you get the alternating bit. You get minus n over 2. So the right-hand side, yeah, the right-hand side just agrees immediately when you do the substitution. But over here, I don't know. So what is this? 1 plus 3n minus 3 halves? Oh, and I didn't do the z yet. Sorry. Anyway, 3n and then minus 3 halves, right? And then here I get like 3n minus 3 halves. But it's a reciprocal. And then here we just get 3n. I just don't see this working out for me. It was supposed to be this. 1 minus qn at the end of the day. Left-hand side is supposed to be 1 minus qn. Yep. So if we can make that happen, then the problem is done. 54. I've got multiples of 3. Anyway, when we let z be this, you'll notice that reciprocal of z is, of course, like this. And you'll get oh, damn it. Did it again. Fuck this. You'll get 1 minus. So I'm hitting this with negative q to the negative half. It's q to the negative 2 there. I get 1 minus a multiple times q to the negative 2. And then here in the middle, you get 1 minus multiple of 3 times... Oh, damn it. Damn it, David. Get it together. All right, I'm supposed to add half here. All right, fine. I did it backwards then. So this was the reciprocal term. If you subtract half from that, you get negative 2. For the non-reciprocal term, regular term, we do get a minus, but if you add half to that, you get negative 1, like that. And then I've got just a multiple. And so the claim is that this mess magically equals 1 minus q to the n. Wow, it's very algebraic, isn't it? It covers every remainder. Mod 3. I almost believe that this is true. Hey, wait a minute. What if we just multiply it out? Is there an easy way to see that this is obvious? I mean, without just... I mean, I guess I can just multiply it out and see, but... This divided by that... Nah, that's not helping me. Well, all right. Yeah, just multiply them out maybe. That's 3n with a q, minus 3n with a q, and the last one is like one level smaller, but we're about to scale it. We're about to... I don't see it yet. Whoa, that's madness, Stucky. We need some LaTeX in this stream. I need to keep like maybe I should sign up on that Myro website so we can actually chat sometimes. All right, I'm gonna be naive. Well, I guess it's not naive. You just wrote it out, huh? Q squared, da 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 da. That's madness. All right, I'm just going to be naive and foil. 1 minus q to the 3n minus q to the 3n. And then we get plus... No, don't foil. Yeah, I don't see it. Oh, you're no, I still don't see it. Yeah, I don't know. First two factors are -2. Oh, wait. Yeah, 3 and -2. I should be adding these things. I guess I thought it would cancel. Minus Q3 is such, which is the right-hand side, huh? Or no, it's this. It's this, yeah. Huh. Well, I'd be happier with 0. But yeah, the one term would give us this junk. Oh, sorry. I did a 0 term. I did it again. Yeah, the one term would give us like 1, and then here you get 2, and then here you get 3. Which I guess I could FOIL out. That's weird. What happened to my q cubed term? Plus q cubed minus q cubed. Why would you do this to me? Well, it's gone. Say goodbye, q cubed. Alright, fine. Goodbye. Plus q to the 4, q5, q6. Well, minus q6. Confusion. No FOIL. Yeah, stop foiling. Well, yeah, so the n equal 2 term two. Looks like, why are we thinking about this? Isn't it just 4? Yeah, 4, 5, 6. Oh yeah, you're right. Stop foiling. Yeah. Of course it is. Right. Yeah, of course it is. Wow. Huh. I wonder what I thought was going to happen. I guess if I finish doing this, it's going to look like this nightmare, right? It's going to look like this, but with a bunch of n's in front of it. So this was a sad approach, what I was doing here. Yeah, thanks, Ducky. Obviously good advice. Yay. All right. That means we did 53 and 54. With little help from Stucky. It's 55. 55. I notice the sum has changed. The indices. I was thinking about this one earlier. Because these cancel. Like, not nicely though. like, there's a, this cancels with that and leaves you with 1 plus q cubed. This cancels with that and leaves you with 1 plus q. But I don't know if that's actually helping me. Q cubed, 1 plus q5. So actually these all cancel and leave you with the previous question, right? Yeah, isn't the left-hand side identical? So how would I get this? Oh, maybe this simplifies? I don't know if you can read that. But I'm thinking the left-hand side, oh no it doesn't, it's not the same. I have 1 plus q, okay. So I have 1 plus all the odds. So for all the odd n, I have basically the same product, but for odd n I have a plus sign. So it's like I replaced q with negative q, maybe. If it's even, it's... If they don't all get canceled. Yeah, they don't all get canceled. Like what happened to 2? 2 didn't even show up anymore. Didn't I cancel it? I think I did. I did. So 2's not even there. So yeah, this is a bad approach that I just said. Still, it looks pretty close to that. Huh. And like, what about 8? 1 minus q to the 8. That never cancels. Damn it. Anyway, I might be able to fidget with something to get 55 going. Yeah, what did he say for 54? Oh yeah, he didn't say anything. He just said plug in this. He just said plug and chug. And 55, he says, is a special case of 53. So I won't spoil it for us. But he seems to say, maybe look at 53. All right, I must leave. My brain. What if I finished foiling? Do you think I would just be miserable? I would not be happy. I can see that. Don't even do it. Yeah, what is going on here? How'd that even happen? Wait, what happened to this guy? Oh, I see. That's not there. This is not there. Oh, right. Yeah, I don't know. I don't know. This 3n is 6n, so this is fine. Then you get itself minus the stuff, and you get like 8 terms. Why would I... How did I get like 8 terms? Oh, because of the cancellation here. So I don't get 8 terms. I guess this guy canceled, but I don't see where. Huh. Well, I also didn't do it quite the same. Yeah, it's almost more... Oh, whatever. It doesn't matter. So yeah, you get itself. I don't know why I'm doing this. You get itself minus q to the 3n. What the hell? Wow. Hmm. Yeah. Hmm. Pretty unwieldy. I guess I was supposed to know not to do this. I was expecting this to magically equal 1 minus q to the n. Well, q3 happened to cancel, right? Like, when you look at, for the case of n equal 1, it's like this last term. It's as if this guy canceled. It got subtracted, q3 times 1. So it's as if this canceled with that. But I'm treating this as q. So things might be sort of backwards. Not really. It's sort of like 1, 2, 3. So yeah, if you hadn't pointed that out, I would have no idea. I would have been trying to do this. If I divide by 1 minus q to the n, I mean, I can see that we get like, what do you get, 3 of these, you get this. So I can see that we're getting like this behavior, but I don't know how that helps me. And then same thing with 6n. I guess that's positive though, for some reason. Wait, did I screw that up? No, I didn't. That one's a 1. So this time, all right, fine. It is what it is, I suppose. So yeah, I would have gotten here, and I would have been confused. So I would have been asking, is it somehow possible that q to the n equals this minus this plus this? Or is it true that anyway, it doesn't have to be true because it's the product overall is equal. I'm not, it's not necessary that this equals that. It just would have been nice. So what I'm saying does not have to be true at all. But like if I divided by qn, if I divided by qn, you'd get a statement like Anyway, this is clearly not true, right? You just get gibberish. So yeah, this doesn't look true to me. So yeah, this wasn't going to happen. Intriguing. Or is it? Sad confusion noises. All right, I better run. Thank you, Stucky, for getting me unstuck. You all have a fantastic evening. I'm going to run away. Go bang my head against a wall to clear my mind. You lads and lasses, thanks for watching, and have yourself a fantastic day. Arrivederci.